about the fourth time I've given this talk, and a few of you have seen it before, so I apologise for that. But I'd first like to thank the organisers, in particular Ho-Ban Chan, for giving us, well, me and everyone, the opportunity to come to Hong Kong. Never been to Hong Kong, never been to Asia, so it's been a good thing to do. So I'm going to start my talk kind of backwards with the acknowledgments. So this was work done before I was at Freiburg, when I was at Leeds in the UK, and I was working with Adam Stokes, who's a postdoc in the group of Alan Feiger. He's more of a mathematical physicist, so that's why this talk moves slightly away from the practical Casimir effect aspects and more towards the mathematical physics, but it is slightly grounded in real life in some respects. So, in keeping with me doing this talk backwards, my introduction is actually the result, because a lot of this talk is going to be quite abstract and mathematical. So what I find is the best way to do it is to present the result first so you can see where we're going, and then I'll explain how it works. So this is what we've done. We've derived an equation which describes perfectly reflecting boundaries for fields with arbitrary spin. So we have various factors here. Okay, I'll use this one as a pointer. Yeah. Okay, so we have various factors here which I can explain. So first we have some products of the normal vector to a surface. So there's more than one normal vector, even just for one surface, which isn't what we expect. We have various Pauli matrices which build the algebra for the field we require, and we have a spinner that describes the field. This could have any spin, so S is the spin divided by 2. Well, it's 2S. So this describes the bag model, which has been mentioned already, for quarks and gluons in a nucleus. It also describes an electromagnetic perfect conductor, and just as another example, which I'll come to what this actually means later, is it describes this hypothesized graviton plate. So this is just a few of the lowest spins that we can describe using this. There's also the spin 3/2, which is in between, but doesn't really apply so much. So the main thing I want to explain is roughly the background of how we got to this equation and roughly how it works. So the formalism we use is this two-spinner calculus, which was invented by B.L. van der Veerden a long time ago, in 1928. And what it exploits is the fact that the complex symplectic group and the proper orthochronous Lorentz group are actually identical. The representations of them are identical up to a phase. So in more grounded language, there's a very close relation between spinners and space-time. And in fact, if you want to be really loose with the language, you can even say that spinners are in some sense the square root of space-time. This is a 2-to-1 correspondence. For every element of space-time, there's 2 spinners. So what we do is just to compare the way we write space-time vectors, so this is a vector in Minkowski space, with the way that this two-spinner calculus expresses spinners. So when we have a vector in Minkowski space, we have 2 spinners in a symplectic space and its conjugate space. And then similarly, we have the dual vector, which in the normal Minkowski description is in the lower index, so normal vector. Well, the not dual vector is the upper index. And similarly, we have 2 more symplectic spaces. And you'll notice that these psi's, everything about which space and whether they're the dual or not, is represented by where this index A is. So instead of just having upper and lower indices, we have barred and not barred. So if I could somehow write in 3 dimensions, I would have upper, lower, forward, back, whatever. But because we have to write in 2 dimensions, we put a bar on them. So it's another sort of degree of freedom for the indices. And just as you get in space-time, you have a conversion rule to get from covariant to contravariant. In the spinner language, you use this symplectic form, which is this alternating thing that works like the metric, so it's alternating, non-degenerate, and so on. And the main advantage for our purposes of this kind of formalism is that spin tensor operations, so the higher the spinners with more than one index basically, become particularly simple and are all encoded within what happens with the indices. So taking, for example, I don't know, the transpose of one of these spin tensors, you just swap the indices, take the Hermitian conjugate, you just put a bar on both indices and swap them. So everything is expressed through the indices. So if you understand the index gymnastics, everything that you need to do from going from one field to the other, spinner, space-time, whatever, can all be done just through the indices, which is quite nice. So what we really care about is the fact that Hermitian matrices have components that are written like this. So you can see that if I do this operation, so go from BAB to B bar, A bar, if A and B were the same symbol, when I do Hermitian conjugation, I get the same thing back again because I just swap them and swap the bar as well. And another important fact for us is that an element of Minkowski space can be arranged into a Hermitian matrix. So this is just the four space-time coordinates arranged in a particular way, which we can also write as the sum as an inner product of the 4 vector with the 4 vector of Pauli matrices. So that's just the Pauli matrices in the 3 slots and an identity in the first slot. So that gives us a way of combining writing Hermitian matrices in a mixed space-time and spinner index form. Okay, so this is the main reason why we're doing any of this. So it allows us to express Minkowski space vectors via Hermitian matrices. And those type of matrices are especially simple in this language. So that's most of the abstract part done. And now we get to see what the actual consequences of this are to real wave equations that we know. So hopefully you recognize this as a statement of the Dirac equation. So all we do is change notation into the 2-spinner form. So here, now sigma mu A bar A is not a matrix, it's just a number. It's 1, 0, minus 1, or plus minus I. So you don't have to worry about commuting gamma matrices or any of that stuff. Everything is just elements of matrices. We go to the next spinner field, which is spin 1. And what you find is that if you arrange the electric and magnetic fields like this, so you form this E plus IB, it's known as the Riemann-Silberstein vector, and then use the components of that in a spinner, what you actually get for Maxwell's equations is this. So these two are equivalent, as you can work out just by substituting in, working out everything. So what you can already see is that to go from one spin to another, you just basically add an index to your spinner. And as long as you know what that spinner means, then you can just build higher and higher fields. So what I actually put into this presentation today was a cartoon of what I really mean. So you can take lower spins. These are the fundamental representations of the Poincaré group. You can take the direct product and you get the field describing a higher spin. And that obeys all the same wave equations as the field with lower spin. So
you have 0 mass for the...
Yes, everything's massless here. So you keep going. You can do the Rarita-Schwinger field, which describes particles of spin 3/2, which, I mean, is a gravitino or a delta baryon, so it doesn't really matter much for practical consequences. But you can see that the expression of it is much more consistent and intuitive relative to the usual formulation of these types of equations. And you go another one, go to the spin 2, which is the graviton field, or at least what it would be if it existed. So you just keep on adding indices, and everything works in this nice way. So then obviously you can write, for general spinner fields, an equation that would describe any of them. And yes, they're all massless. And I don't know if there's any other way of writing a general spinner field equation. So just a brief detour back to the abstract stuff. My co-author actually made this up with everything anyone has said Poincare pyramid before. And what this is, it just shows you the hierarchy of all the fields and potentials that we use. So in the middle column, we have potentials that are all real, that are, so I know these are complex, right, no, these are the real valued ones, sorry, I'm confused now. And these numbers just label what and how many representations of the Poincare group you're taking a product of. But what's more useful for our purposes is this sort of outer representations where the two spinner is attained just by adding indices. So for example, we have a complex quantity here, this is the E plus IB. We have the left and right-handed vial spinners, which are in general complex. And I don't know of any other ways of expressing these two. This is what we're doing, we're just carrying that on. So, we're now done with wave equations. So now I can talk about what this presentation is actually about, which is boundary conditions. So get rid of these. And look first at the so-called bag model boundary condition, which describes quarks and gluons in the nucleus. So all that does is say that the normal component of the electromagnetic, well, the Dirac-4 current at surface is 0. And that's what this says. It's just a slight rearrangement of that using the definition of the current. So we literally just change notation, put it in the two-spinner form, and then taking inspiration from how the wave equations worked, we take a logical leap and postulate that the Maxwell boundary conditions at a perfect conductor must be of this form, because we just want to add indices to our spinner, and we want to make everything match up with respect to the indices. So then you substitute in the known form of psi, and obviously the Pauli matrices and the normal vectors, and you do really get back to this. So this logical leap seems to work. So we get a tick there. So you keep going, keep adding indices. You get this equation for the Rorita-Schwinger field. There are no real boundary conditions in the literature for this already. I mean, people have worked with the field, but they just always say, I don't know, periodic boundary conditions, whatever. They don't think about physical boundary conditions for these types of fields. So we go to another one for the graviton, and that's equivalent to this gravito electromagnetic field. So there's an analogy between linearized gravity and electromagnetism. And these are gravito-electric and gravito-magnetic fields, and our boundary condition we can use for those. So, fairly obviously, there's no obvious way, given all this, of expressing a generalized boundary condition. If you use our language, then you get then you get this, which is what I showed you on the first slide. So it came from taking the Dirac boundary condition and just building up, like Lego, the indices, and taking as many consistency checks as we can on the way, and we end up with this formula, which is what I showed you. So now, in the next 5 to 10 minutes, I'm just going to talk about a couple of consequences of this. One nice property is that we have the multiple normal vectors here. So if you take a fermionic field, that will have an odd number of normal vectors. If then if you then apply this to this kind of standard parallel plate system, at this end of the system, you will get an odd number of factors of minus n, so you get an overall minus relative to this end. So that basically means you get anti-symmetric solutions, which is a statement from the Pauli exclusion principle. So that's quite nice, and it reproduces all the fermionic Casimir effects that you'd expect. So the exclusion principle is kind of built into here through the way the algebra works. This also tells us, there's a bit more work to show this, but that all bosonic Casimir forces between perfect reflectors are the same, and the same thing goes for fermionic Casimir forces. So we have our standard, very well-known expression for the bosonic, and they're almost as well-known for fermionic. This is all in natural units, obviously. So this is Casimir's original result, and this is another well-known result. And all we did here was prove that for any fermion, this has to hold, and for any boson, this has to hold, under the assumption of perfect reflection. But now what if we take away perfect reflection? We would inevitably gain, in the photon case at least, a dependence on the fine structure constant, so the degree to which electromagnetism couples to matter. If we assume it's not perfect, we have to know how much it actually is. So, that's what I just said. So, the normal electromagnetic Casimir effect between both reflectors is actually the alpha goes to infinity limit of the finite alpha result, alpha being the fine structure constant. So just the electromagnetic coupling. And that's one of the kind of not mysterious, one of the extraordinary things about Casimir forces is that they remain finite even in the limit of infinite coupling, as other processes wouldn't. Okay? So, for to look at imperfect reflection for other fields is going to be quite complicated. So I'm going to talk about a work that someone else has done, just briefly, where they take the linearized gravitational field, so you take the metric parameterized by some u, and expand it around that, so you get the flat space metric plus a linear term and another metric. You then put this in use this in the Einstein field equations in a transverse traceless gauge. What you get is this wave equation, which is the wave equation for gravitational waves, which, of course, exist, as we know. So you can then quantize this field. It's just a wave equation. This was done a long time ago. It's just the quantization of basically the same as the quantization of an electromagnetic field. The way he did it originally here, Gupta, you get, I think it's 10 or 11 independent polarizations of graviton, and that reduces down to only 2. Or you can make the analogy with electromagnetism, and then you're already in the 2 polarization picture. So given a quantized field that's similar to electromagnetism, or in fact any quantized field, you can have gravitational vacuum fluctuations. So consequently, you would expect a gravitational Casimir effect. So that's what this paper did a little while ago. Some of you mentioned it to me already, actually, when you found out what my talk was about. So this is a purported gravitational Casimir effect, where the author basically derives a Lifshitz formula, but for the gravitational field. So what these 2 reflection coefficients are is the reflection coefficients for the so-called plus and cross polarizations of gravitational waves. So the plus, when acting on a circle of test masses, stretches it one way, and the cross one stretches it the diagonal direction with respect to the first one. And as I'm sure a lot of you can already see, this is identical to electromagnetism, just with the 2 polarizations changed to the 2 gravitational polarizations, like you'd expect. So yeah, in the limit, in the strong coupling limit, you recover our bosonic Casimir force. The thing is, the functional form of this is basically unknown. And in this paper, they talk about the Heisenberg Coulomb effect, which is very controversial. I don't have time to go into here. But that suggests that there could be strong reflection of gravitational waves from a particular superconductor. But to their credit in this paper, they say it's this calculation is more a demonstration that this Heisenberg-Coulomb effect can't be true, rather than a test for the existence of gravitons. So, for example, because we haven't seen this, because it's the same strength as the electromagnetic force, then it's a proof that the condensed matter ideas behind this are not applicable to the real world. So, what do we want to do next? Well, we want to do imperfect reflection properly for ball spinor fields, because what I mentioned previously only applies to gravitons, rather. So, the reason we want to do that is because imperfect reflection in some kinds of systems can do unexpected things. And just an example of that from my previous work, this is going back to my PhD now with Claudia Eberlein, where we looked at this surface-dependent anomalous magnetic moment of the electron near a surface. So this is my cartoon representation of that. where the exchanged virtual photon passes through matter and has its propagator altered, basically. And what we found was that relative to the perfect reflector result, which Gabriel Barton derived a long time ago, there can be significant enhancements when you take into account realistic materials. For example, this peak here can be higher than plotted here by about a factor of 1,000. So we've gained at least 3 orders of magnitude by including imperfect reflection, and that's to do with the way with the particular excitation spectra of a trapped electron. So yeah, just as a demonstration of what we had here. For these kinds of distances near to a particularly tuned surface, a particular type of semiconductor, the surface dependence of the magnetic moment could turn up roughly in these kinds of digits. So it's not something they'll see in G-factor measurements already because they don't have those particular surfaces and because the penning traps they use are of centimeter scale. But if you wanted to design an experiment to see the surface dependence of the anomalous magnetic moment, then we think in principle you could, at least given the right materials. So my point of mentioning this here is that imperfect reflection doesn't just mean everything will get less, as you might expect, due to weaker coupling. It can have completely opposite. I mean, here it even changes the sign of the force, of the effect. So this is my kind of state of the art, which is also ultimately my summary. So this kind of, basically here, where almost every talk so far has been working, so realistic surfaces, which is what I mean by perfect reflection, thinking about the photonic Casimir effect, and obviously perfect reflection and for photons and perfect reflection for fermions has already been studied fairly extensively. There are a few works that do the imperfect reflection for fermions, but these are in quite an early stage so far. All the results differ by quite a lot, and there's no real consensus. So these two fields, the graviton field and the even less useful field, the 3/2, were what we did, and also the arbitrary spin. And this graviton paper is here. So what's still missing is the 3/2 for imperfect reflection, which presumably could be done, but it's not so much interest. What is of interest is the arbitrary spin imperfect reflection calculation, which we are currently sort of working on, and we hope to make some progress soon. And the main reason we want to do that is because if you can describe all these things in a unified way, you can take all the massive number of techniques that have been developed for the normal photonic Casimir force and use them in this unified formalism to try and investigate the effects of imperfectly reflecting media on spinor fields. So this is also my summary. The main thing I like about this is that it's so elegant. You can just literally build up the fields like Lego, like I mentioned, and as I've just said, it's a promising route to the further development of the theory of spinor fields. And that's all.
When considered in the bag, you gave the boundary condition for the perfect conductor. But if you go back to the MIT bag, the situation was the other way around, because the external medium was a perfect diamagnetic medium, in which epsilon and mu changed place.
Okay, well, yeah.
That has not nothing to say.
No, I mean, all we really care about is that it reflects the current, that there's no component of the current through the surface. So, I guess there could be a slight ambiguity in whether that comes from an epsilon or a mu being large, whether it's a perfectly reflecting magnetic material or perfectly reflecting electric material. But in the electromagnetic case, we do get that it's the epsilon to infinity conversion.
Well, that was my point. With the electromagnetic case, you can have either a perfect electric conductor or perfect, and yet if you have an interaction between one type and one of the other type, it changes the sign of force.
Yeah.
So what you say, there's only one sign, there's only one result. There's certainly not certainly more than one
Okay,
in general,
so
so I don't understand what you mean by strong coupling. It's just not, it's not the magnitude of R that matters, the sign of R also matters.
yes. So
I don't see where that comes from.
okay, so yeah, I think perhaps I should say all bosonic.
So they don't all have the same force, that's not true.
Yeah, okay, but perhaps I should have been more careful with the statement that all bosonic, all sort of materials that can be described by a bag model, which seems to be equivalent to having an infinite epsilon, then they're all going to be the same, right? So, see what I mean?
But I'm not sure how that generalizes to greater than spin 1, or maybe more than. How do you know there's just two possibilities in higher spin?
Basically, I don't. But what I can say is that there's quite often not immediate analog of epsilon and mu in higher spins. So I don't know if that would be a peculiarity of electromagnetism or if it would transfer to higher spins. I just don't know.
This might be a slightly unfair question because it's slightly off topic, but I saw that you can, to form a one-spin field, you combined two half-spinners in your formula. And this reminds me of the formation of Cooper pairs from two electrons in a superconductor. Do you have any thoughts about how your formulism could maybe help study that area?
I think the sense in which they're combined here is so abstract that it doesn't particularly match up to, in any sense, to having two, actual fermions in space being combined with each other in some way. So maybe formally there might be some similarities, but as for underlying physics, I would guess not. But I haven't thought about that.
I have a question about the imperfect boundary conditions, the imperfect reflections. As you quite rightly said, that actually means that you have an interaction between your whatever spinor field or spin its half field with matter, which is a particular spinor field. Is there any chance that you can sort of also generalize that to any kind of interactions between sort of bosonic and other fermionic fields that would constitute these imperfect boundary conditions?
That obviously would be very difficult. I think the best we can do in the kind of reasonable future is to come up with an analog of epsilon or mu or both for materials that may interact with higher spin fields, and then hopefully try and put that on a more fundamental ground by considering the actual interactions of what actual particles are going in there. In the same way you can consider microscopic and macroscopic formulations of a bulk in electromagnetism. I think we would start off with the bulk and not think about a microscopic one yet. But ultimately that would be a goal.
Is there a way to generalize this to anyons?
To what?
Anyons. Non-fermions from boson.
I really don't know. I would guess not. Exactly because you say they're not bosons or fermions, and I don't know. That's right. So it's neither a boson nor a fermion. By building up essentially from spin half fermions. With that.
Define the reflection coefficient.
Yeah. I don't know anything about anyways.
There's one more. Right here.
Yeah, well, my question is related to a previous one. I think that the limitation of this general method is to free fields, in a way.
Yeah. Yes.
No.
No mass.
If you introduce, and massless, if you introduce minimal coupling, for instance, just the minimal coupling, then you have to proceed. You don't have a general way of doing that, and so this is a limitation.
But I mean, a lot of the way we got this published was to concentrate on the spin half and spin one, which the spin one obviously is massless, if you're talking about photons, and the spin half, for example, for nuclear physics, the quarks inside the nucleus in this bag model can be considered massless just because of the energy scales. So even just as a unification of those two, there are practical, real things you can do in the non-interacting case. But I agree, the other higher ones would be very difficult in this formalism.
Questions?
What would be a perfect reflection for gravitons? How could they thought about it?
Well, okay. I anticipated this question. So, this is the claims in this controversial Heisenberg-Coulomb effect. So that these Cooper pairs are delocalized. We don't understand how space-time curvature, so gravitons, if you think space-time curvature as a field, then quantize that as a graviton. So that's basically the same thing. We don't know the effect that space-time curvature has on extended delocalized objects. So that leads to these supercurrents, they say, which could dramatically enhance reactivity just by making it easier for the Cooper pairs to be moved away from ion cores. So it would be something in a superconductor you would see, but it relies on quite exotic models of how delocalized objects are acted on by curved spacetime.
Yeah. Just another question about the same thing. So you suggested the graviton as an interesting possible physical example. Then the calculation is for linearized gravity. Thinking obviously the gravitons, if it exists, are not linear and self-interacting. So would that affect?
That would affect it.
Affect it.
And in fact, there are generalizations of the, because I talked about gluons here, and they're self-interacting really as well. And there are generalizations of the bag model to include self-interacting gluons. So perhaps one could take the same route to include the self-interaction of gravitons, but I don't know how to go beyond really the kind of linearized approximation, or whether that would even do it. I'm not sure.
Actually, more than comment question, I would say. I saw recently there was a paper by Larry Ford on the equivalent of van der Waals interaction in gravitational fields.
Yes.
So I did look through the paper and I had forgotten that one. But generally, what you do when you go from Casimir to Casimir polar, you take the dilute limit. And I wonder if those two papers and the one of Larry Ford could be related by this kind of procedure, and if there is something that you can learn from Ford's paper or your theory.
Yes, I've seen that paper, and actually yeah, I don't see any reason why not, especially because I think in that paper it uses effectively the gravito-electromagnetism approach. So there's really no reason why not. You can't just transfer all the process from going from the dilute limit to the bulk one. No, sorry, from the individual atoms to a bulk. There's no reason why you couldn't transfer that to the graviton case. So I've seen that paper, and I've kind of read it, but I think that would probably work.
Sorry.
So thanks, Francesco, for raising this point. For the sake of history, I would like to recognize Matt Weber-Honstein, who made the same calculation as Gupta, quantizing linearized gravity, around 1930.
Oh, wow.
Yeah, it was everything, as you mentioned from Gupta, the polarization and everything, canonical. And so I was thank you for the reference of Van Woorden, because 28 is just 2 years after quantum mechanics. Right? Yeah, talking about two speeders, but very from a mathematical viewpoint only.
Yes, sure. Yeah. And in German as well.
Yeah. My thing is German and Russian. Yeah. Deutschland.
Yeah.
Another question? No more question. So the session concludes, but maybe Coulomb does. Nelson?
So I was hoping that the weather would be nice yesterday, but it didn't turn out that way. So in case, I think that you couldn't see anything at the peak. So if you are staying a few more days here, I would strongly suggest you go back there yourself. I think it's really worth it. Okay, so about the schedule. Just some modification. The last talk originally was Alejandro Rodriguez. He's not able to come. So we have replaced the talk by Afi Shamon. And this might not be correct on your printout, so just to let you know. And for the rest of today, we have the poster session after this, and then dinner. And dinner is by invitation, and if you are not sure whether you are on dinner, please check the list outside with Nancy. And the bus will leave at 6:15. And there will be 2 buses, because one bus is not enough to carry all of us. If you are coming back to the conference lodge, you don't need to worry. But we have 2 buses, one big, one small. Both of them will go to the dinner venue, the restaurant. The big one will only come back to the conference lodge. The small one will come back to the conference lodge and then go to Hang Hao MTR station. So that is for those of you who may be staying off campus or might be up for more partying after the event. Okay? Okay, so that is for the bus.